Okay, so our next topic is functions, and the definition that you'll see in a book is a function is a relationship between two variables such that each value of the independent variable, for each value of the independent variable, there corresponds exactly one value of the dependent variable. And the notation we use is y equals f of x. Sometimes we say y equals x squared. Might sometimes say f of x equals x squared. They're kind of independent. F of x is kind of the function. Y is the y coordinate on the xy coordinate plane. They can kind of be used interchangeably, either f of x or y. So now there are things that we're kind of used to. We might think of functions, but they're not functions. So I'm just going to show you one. So, and what do you call those? You might call them equations, you might call them relations, but they're not functions in the strict definition. So if I had x squared plus y squared equals 4 or 16, and I drew that relationship, it's a circle with the origin, or the center of the origin, with a radius of 4 units, so something like that. So, it's still a curve. There's still a relationship between x and y. The reason it's not a function is if I draw a vertical line that for the given, say for x equals 1, for example, if I move this over to x equals 1, you'll see that there are two values of the independent variable. You'll also notice that this is not explicitly solved for y. If you did that, you'd say y squared equals 16 minus x squared, and then you take the square root. And a lot of times people forget to do this, but you'd have a plus or minus. So the plus part would be the top part, and the negative part would be the bottom part. So these are functions. So these are functions, but this is not a function, and this is not a function. That's not a function either. So if I took half of this curve, you can see that I'd only intersect this top half once and the bottom half once. So there are lots of relationships, ellipses, hyperbolas, even something like x equals y squared instead of y equals x squared. So y equals x squared is a function, but x equals y squared, which looks like this, it's just a parabola on its side. It's not a function because if you draw a vertical line, you're going to cross it two places. So now there are two important properties of a function. One is the domain, and the domain of a function is the set of all x values of the independent variable for which the function is defined. If x is in the domain of f, then f is said to be defined at x. If x is not in the domain of f, f is said to be undefined at x. So basically what that means is for a given function, either there are certain possible values of x that are possible, or you could actually personally define the domain to include just a certain interval in x values. So sometimes it's kind of the default domain. So let me just give you an example of that. So let's say y equals the square root of x plus 2. So the domain of a function is the set of all values of the independent variable, which is x, for which the function is defined. Well, the square root function can only be defined when the argument is positive. So to figure out the domain, what I do is I say that x plus 2 has to be greater than or equal to 0, because we can't take the square root of a negative number. And if you solve this inequality, you just subtract 2 from both sides, you get x is greater than negative 2. That's the domain. Now I could say y equals the square root of x, and specifically say, you know, that x has to be greater than 5 and less than 15, or less than or equal to 15. So this would also be the domain, but I'm specifying that domain, which is a smaller subset of this. So 5 is greater than negative 2, and 15 is greater than negative 2. So during this, in this interval, it's always greater than the domain determined by what is possible. Now the range is a function is the set of all values outputs assumed by the dependent variable. That is the set of all function values. So it's basically the allowable y values. Usually if you set the domain, then you can set the range. So again, back to the square root function. The square root of a positive, it has to be positive, so this argument has to be positive. So the square root of a positive number is always positive. So we would say, in this case, the range is y is greater than or equal to 0, because the square root of something, the square root of a positive number has to be greater than 0. Now you wouldn't normally limit the range and then figure out what the domain is. Usually limit the domain and then the range is kind of set. So, you know, for this second example, what you would do is you would plug in these numbers. So you'd say y of 5 is the square root of 5 plus 2, which is the square root of 7, and y is 15. Y of 15 would be the square root of 15 plus 2, which is 17, square root of 17. So in this particular case, the range would be that y is greater than or equal to 7 and less than or equal to 17. So this domain would result in that range. Now for a lot of things that we do in pre-calculus and calculus, we're dealing with polynomials. So typically polynomials have a range that goes from negative infinity to positive infinity. You can pretty much put anything in here. You can square any number. You can add any number squared to a single number, and so this would be the domain. Now the range is a little more tricky because, you know, these parabolas, especially when you have a positive coefficient here, you know, they can be like this, they could be like this, and so you have to figure out what this minimum point is. And so the range would take from this value anything positive beyond, more positive than that. And the way you would do that is you had to figure out what the vertices of this parabola are, which we'll talk about later, but I'm just going to show you now. What you would do is you would complete the square on the right hand side. So you take the coefficient in front of x, divide by 2, square it, so that's 1/4. So you get plus 1/4, and then you subtract a fourth. And then this can be collapsed into a perfect square. So you have x plus 1/2 quantity squared. Here we have 6 minus a fourth, which is going to be negative 25 fourths. So take 4 times 6, that's 24. 24 fourths minus 1/4, negative 25 fourths. So negative 24 minus 1 is negative 25. Okay, so for this is what's called the standard form. the vertex is going to be at x equals -1/2 and y equals -25/4. So for the range, you take this number, and the y values would be always greater than this y value for the vertex. So in this case, the domain of this equation is all real numbers, but the range would be y is greater than or equal to -25/4. And I know it's greater than because this coefficient is positive. If it was this coefficient in front of the x squared were negative, then this would be the maximum value, and everything would go down. Okay, so here, this is talking about implied domain. So this is assuming that I'm not specifying the domain. And we've already looked at these two problems. So for a polynomial, the implied domain is all real numbers. Notice I don't put equal to here because nothing can ever equal negative or positive infinity. Another way of representing this is to put it in ordered pairs. So you put a parenthesis, and this means that it's not equal to -infinity, and so that gives you the lower bound, that gives you the upper bound. This tells you it's not equal to. Now here we said that the argument of the square root function had to be positive, so x has to be greater than or equal to 0. So that's the domain. Here's the domain. This is the domain. This is the domain. Another way of representing this would be 0, positive infinity, square bracket. And that's actually wrong. It's the other way around. Square bracket goes at 0. So what that means is that it can equal 0, but it can't equal infinity. So another way of writing this would be that x is greater than 0 but less than infinity. By leaving this one side undefined, it's assuming that it's going all the way to infinity. Okay, we got one more here. So in reciprocal functions like this one, the limitation on the domain is that the denominator cannot be 0. So there's a few ways you could do this. One would be to say all real numbers except x equals 4, because that'll make the denominator go to 0. You could say from -infinity to 4, and from 4 to positive infinity. So I'm not including 4. Let's see if there's any other way. You could also, I guess, say from -infinity to positive infinity except x equals 4. You could use the notation here. So there you would have -infinity, 4, parenthesis, and 4, positive infinity, parenthesis. So saying that it can't equal 4. Okay, so it says problem 87 on page 38. So here we have an open box of maximum volume is made from a square piece of material 24 centimeters on the side by cutting equal squares from the corners and turning up the sides. Okay, so let me explain what's going on there. So you have a square material. So it's made of a square material, and this dimension here is 24 centimeters, and this dimension is 24 centimeters. And what you do is you cut out a little square in the corner, in each corner, and then you fold up on this crease and this crease and this crease and this crease. So these fold up as the sides of a open tray, basically. And this is the dimension that you're cutting in the corner. And this dimension here, which is x, is going to be the height. This will be the height of the tray. And what they show is this table, which is height, which actually, according to our diagram, is x, and the volume, we use v. That's the volume, three-dimensional volume of the tray. So it's this dimension times the height. And if you generate a table, you get something like this. So these are the different heights. And at some point, you get a maximum volume. So we get 484 cubic centimeters, 800 cubic centimeters, 972 cubic centimeters, 1024, 980, 864. So there's a maximum point here somewhere. So if you think about what does that look like, when you have zero, when the height is 0, you have 0 volume, and then it's going to go up, it's going to reach some maximum, and it's going to come back down. And at some point, if the walls are so high you don't actually have any volume, it comes back down again. And this point here is around 4 inches or 4 centimeters. I'm not sure where it ends up crossing. So, and then this would be the volume, which would be 1024. And again, I'm not sure if that is the exact maximum. It might be slightly different. And actually, we'll use calculus to figure out. You could calculate the exact dimensions to get that maximum volume, but this is kind of eyeballing it. So part A says use the table to estimate the maximum volume. Well, that would be this value, 1024 cubic centimeters. Part B says plot the points, so I'm just kind of approximating it. Does the relationship defined by the ordered pairs represent a function? So yes, because if I draw this vertical line anywhere within the domain, which goes from 0 to something, probably 12, because if you had these heights 12, then there wouldn't be anything left over to be inside. So this is probably 12. But you can see it only crosses the curve one time, because that happens for every value of x. There's only one value of y, so it is a function. And it says if v is a function of x, write the function and determine its domain. So what you can do is the volume of this construction is going to be the height, which is x. And then if this is x and this is x, then this dimension, what's left over, is 24 minus 2x. And the same thing over here. This is going to be 24 minus 2x. So the total volume is the height times this times that. So that's the width and the length, and this part's the height. So it would be 24 minus 2x and 24 minus 2x. And you actually know this is a third order equation, so I think actually this would have it goes off, but these are the only realistic values. The other ones are not valid answers. So let's multiply this thing out. So you'd have x. If you do FOIL, you'd have 24 times 24, which is, I forgot what it is. Let me get my calculator out. 24 times 24 is 576. Then you have 24 times 2, which is 48, and you got two of those, inner and outer, so that 48 times 2 is 96. So you get minus 96x plus 2x times 2x is 4x squared. And then you can multiply by x everything, and I'm going to put the biggest terms first. So you get 4x cubed minus 96x squared plus 576x. So that's the function. The volume is a function of x. And there's some homework. So if these numbers are different than your assignment sheet, just use the assignment sheet.